Welcome to my classroom. I am Nestle. In this video, I shall try to explain the ion movements, ion currents at the resting membrane potential in cells with a constant resting membrane potential. Most of the cells in our body have a constant resting membrane potential. There is a small group of cells with a resting membrane potential that changes in time and reaches the threshold. These cells are called pacemaker cells. This video is for the cells with a constant resting membrane potential. So let us start. Here we see the voltage time graphic. It's a graphic that is very commonly used when we talk about bioelectrical potentials. In horizontal axis is time in milliseconds, and in vertical axis is voltage membrane, the membrane potential in millivolts. This graphic shows what happens to the membrane potential as time goes on. We have two recordings here. Cell number 1 has a constant resting membrane potential at -80 millivolts, and cell number 2 has a constant resting membrane potential at -70 millivolts. So we do not see any change in the potential as time goes on. These cells are the cell number 1 and the cell number 4 from the video of resting membrane, from the video where we discussed the resting membrane potential. So we know from that discussion that cell number 1 has only open channels only for potassium at resting membrane potential, and cell number 2 has open ion channels for both potassium and sodium at resting membrane potential. We know that there are some open channels in these cells, and if you can remember from that video, Nernst potential of sodium is +61, Nernst potential of potassium is -80 millivolt. If there are some open ion channels in these cells, the question is there any ion current taking place? At this point, we need to remember that there are two conditions, two requirements for an ion current, ion movement to take place. One is an open channel. The second one is a force that pushes the ion through these channels. So we know that there are some open channels in these two cells. What about the electrochemical driving force for the ions? Let us discuss the electrochemical driving force to understand if there is any ion movement in these cells. I start with cell number 1. We know that potassium is high in the cell, so the chemical force represented by a black arrow must be pushing potassium from high to low concentration, and our arrow points outward. What is the size of this force? It is determined by the Nernst potential of potassium, and it is 80 millivolts. What about the electrical force? Electrical force is the resting membrane potential, and at the and at the resting membrane potential level, the cell has negativity on the inside, so potassium ions, being positive, are going to be pulled inward by the electrical force. And what is the amplitude of this force? It is the resting membrane potential. It is 80 millivolts. So we have a chemical force pushing potassium outward, Nernst potential 80 millivolt, and we have another force pulling potassium inward, resting membrane potential 80 millivolt. What is the net force represented by green? It is 0. So in this cell there are open channels for potassium at rest, but there is no net electrochemical force for potassium. This means there is no net potassium current at rest in this cell. The word net is important because there may be a few potassium ions leaving the cell, a few potassium ions entering the cell, but there is no net movement in any direction. The movements in both directions are the same. So we say that in this cell there is no net potassium movement, and the only channels that are present here belong to potassium, so we can generalize this to all of the ions. So no net ion movement is present either in this cell. Let us move. A condition like this is called equilibrium. Everything is smooth. in a cell like this, and a condition like this in physiology is called equilibrium. What about the second cell? In the second cell there are both potassium and sodium open channels. So let us start discussing potassium. The same story applies, that there's a high potassium concentration, so the chemical force must be pushing potassium out of the cell. What is the amplitude of this force? It's given us by the Nernst potentials, it's 80 millivolt. What about the electrical force? It is the resting membrane potential minus 70. Interior of the cell is negatively charged, so my arrow must be pointing inward. Negative charges will be pulling positively charged potassium ions inward. What is the size of it? It is the resting membrane potential, 70 millivolt. So in this cell, what is the net electrochemical force for potassium? It is 10 millivolt pushing potassium outward, and I have placed this 10 millivolt here in our formula. Next ion is sodium. For sodium, we know that sodium is high in concentration outside, so the chemical force represented by a black arrow for sodium must be pushing sodium in. And what is the amplitude of this force? It's the Nernst potential, 61 millivolt. The electrical force is the same, it's the resting membrane potential. Since sodium carries positive charges and the interior of the cell is negative, this electrical force will be pulling sodium into the cell. What is the amplitude of it? It is 70 millivolts. So we have a 60 millivolt chemical force and a 61 millivolt chemical force and a 70 millivolt electrical force. So the net electrochemical force is huge here. If you see with the large green arrow, 131 millivolt electrochemical force is pushing sodium into the cell, and I have placed this value in our formula. So we see here that there is a constant movement of potassium outward and sodium inward, but the resting membrane potential is not changing. If potassium is moving out, the cell may become more negative on the inside. If sodium is moving in, the cell may become more positive or less negative on the inside. But we see that it is constant. There can be only one explanation for this, and it is the number of positive charges that go out by potassium movement must be equal to the number of positive charges going in by sodium movement. Only in this case, the resting membrane potential can be steady, constant. So we can express this with our formula as well. The current is equal to conductance times electrochemical force. A big potassium conductance multiplied by a small electrochemical force gives us the total number of positive charges leaving the cell. A small conductance for sodium and a big electrochemical force, 131 millivolts, gives us the total number of positive charges going into the cell with sodium. And these two, the total number of potassium leaving is equal to the total number of sodium entering the cell. So, but we see in this formula that the resting membrane potential stays constant, but this is not the whole of the story. This cell is even more complicated. If there's a lot of potassium going out and sodium going in, they may not be a lot, but in time this will accumulate, and in long time potassium concentration on the cell may fall, or sodium concentration outside the cell may fall. But it is extremely important to have a high concentration of potassium in the cell, sodium outside the cell. We cannot take a risk of a decrease in these concentrations. At this point, sodium-potassium ATPase comes into action. Whenever sodium amount inside the cell starts increasing, sodium-potassium ATPase activity starts increasing, and this pump puts sodium outward back to where it belongs, and it brings potassium inward where it belongs. So sodium-potassium ATPase is very important. It's protecting here in this position the higher concentration of potassium inside and sodium outside. To understand the importance of sodium-potassium ATPase, we can remember this sentence. The total amount of ATP produced in our body, 50% of this total amount, or more than 50% is used by sodium-potassium ATPase. So it's a very, very, very important enzyme protein for our body. So in the first cell, the story is shorter. No potassium movement and there's equilibrium. It's more of a silent cell. But in this cell, although the resting membrane potential is constant, behind the curtain lots of things are happening. Potassium is going out, sodium is moving in. This is increasing the activity of sodium-potassium ATPase. A lot is going on behind constant membrane potential. So this is why this cannot be called an equilibrium. In physiology, a condition like this is called a special type. It's a steady state. So in this video, I have tried to explain the ion movements during the resting membrane potential in the cells with a steady or a constant resting membrane potential. I hope it has been useful. Thank you for watching.